Hello my dear students, welcome to the session. Students, last class we discussed up to 5th problem in the classroom workbook, application of differential equations. Now let us look at the 6th problem which was asked in IES, okay, exam. What is asking here? Is asking I of t for t greater than or equal to 0, okay. So I already explained you that whenever time response is asked, I of t is nothing but what? Time response. Whenever time response is asked, you have two procedures, right? There are two kinds of problems actually have, two categories. Type 1 category is like a first order system, okay, first order network with a step input excitation. Step input excitation, and it is a first order because RL circuit, therefore definitely you can deal with the formula. I told you already, other than the type 1 category, you have to go for what? S domain equivalent circuit, that we will discuss later, okay? So anyway, this one now, we are going to solve this problem using the formula. The formula is very simple. I of t is equal to I of infinity minus I of infinity minus I of 0 plus into this one, okay, this particular part into e power minus t by tau. So let me calculate for t equal to 0 plus what is current and what is current for t equal to infinity, okay. So for I of 0 plus I would like to deal with. Whenever 0 plus conditions are required, first we deal with t equal to 0 minus. T equal to 0 minus, what is I? First you look at that. I is current through the inductor. Yes or no, all of you? Current through the resistor it might be, but you must take current through the inductor. I told you already. Current through resistor will follow current through inductor. Therefore, current through inductor must be taken. Therefore, in the first step itself, current through the inductor may not change instantaneously. So t equal to 0 minus, if you calculate here, the same thing will be okay for what? T equal to 0 plus, because both the conditions are same. Current to the inductor may not change instantaneously. Therefore, what is I of 0 minus? What is the position of the switch? Switch is initially closed. At t equal to 0, you are opening. When you have a closed position, here, and this is acting like a short circuit, this is closed, this is short circuit, and you would like to calculate current through this particular inductor, that is nothing but short circuit, okay, that is nothing but inductor. So what is happening here? This entire voltage, because it is short circuit, this entire 10 voltage is appearing across what? 20 ohm. And this is in closed position, therefore the 10 volts will appear across what? 20 ohm. So 10 by 20 will give you how much here? 1 by 2 ampere. That 1 by 2 ampere is flowing through what? 1 Henry inductor, that is short circuit actually here. Therefore, I of 0 minus is, okay, 10 by 20, that is nothing but 0.5 ampere. Understand all of you, okay? Well, now I of infinity I would like to go with. What is I of infinity? Now, switch is open, inductor is acting like a short circuit. Again, switch is open. Now current flowing through the inductor is nothing but current at 20. This time, when switch is open, 30 and 20 are in series. 20 and 10, two sources. They're connected back to back here. That means they're in series. 20 plus 10, 30. 30 volts divided by 30 plus 20, 50 ohm. Okay, therefore, I of infinity, the t equal to infinity conditions you would like to. So, I of infinity is 10 plus 20 divided by, how much it is? 30 plus 20. So, 30 plus 20. So, this is 30 divided by 50. Okay. 5 6 ja 0.6 ampere. Okay. Now I would like to go with tau for t greater than 0. I told you already, tau for t greater than 0. Your response required is for t greater than 0. Therefore, the tau should also be calculated for t greater than 0. And what is tau formula actually here? Tau is nothing but L equivalent by RTH. L equivalent and RTH both must be calculated for t greater than 0. So for L equivalent means what? Only one inductor is there. Okay. Therefore, L equivalent, here it is 1 Henry. RTH for t greater than 0 again. So what is that RTH? T greater than 0, the switch is open. Both these sources are replaced by the short circuits. In the process of finding RTH, definitely you have to suppress all independent sources. This is open, shorted, shorted. Looking into the network through L equivalent terminals, load terminals, but L equivalent terminals here. You are looking into the network through L equivalent terminals here. This is open. You are looking at the network through L equivalent terminals. This is shorted, this is shorted, this is open. These two are in series. Therefore, 30 plus 20. Nothing but 50. Therefore, if you substitute here all these values, so 1 by 50, that is second. So 1 by tau is usually your requirement. That is nothing but 50 second inverse. Clear? Let us substitute this in this particular formula. Then what will you get, Nana? Therefore, I of t is equal to, what do you get? I of infinity is how much here? 0.6. I of 0 plus is how much? 0.5. Therefore, 0.6 minus 0.6 minus 0.5 into e power minus 50t. Look at this. I of infinity is 0.6. So 0.6 minus 0.6 minus 0.5. Nothing but 0.1 here. So therefore, 0.6 minus 0.1 e power minus t by tau. Minus t by tau is nothing but how much here? So you got here 50t minus 50t. This is what your response. Is it clear, all of you? Okay. So therefore, please note down quickly. Then we will move on to another problem here. Seventh problem here. Please quickly move on that. Complete that. Quickly complete. Okay, I hope you finished this. Now let us move on to another problem. Question number 7, classroom workbook. Okay, Vx for all time t is asking what? Vx for all time t. All time t is nothing but what? All time t is nothing but what? Is asking Vx for all time t is nothing but t less than 0. What is Vx? Okay. For t less than 0, what? For t greater than or equal to 0 is also what is that value? Okay. This is nothing but Vx of t. So let me write clearly here. Vx of t for all time t is nothing but Vx of t for all time t is nothing but what is the value of Vx for t less than 0 and what is the value of that Vx for t greater than or equal to 0. Understand, all of you? Okay. Whenever the question is asked for all time t, that is a way you need to look into that problem. Okay. So now let us try to find it. T less than 0 is nothing but what? Actually, in our assumption, in the transient analysis, we made an assumption that t equal to 0 minus conditions and t less than 0 conditions both are same. T less than 0 is nothing but what? Until the disturbance takes place, the network is assumed to be in steady state. Okay, the network was assumed to be what? In steady state. So t less than 0 is nothing but what? T equal to minus infinity. Nothing but t equal to 0 minus conditions. Therefore, that's not a big deal. You can easily calculate. Okay, but now this one, t greater than or equal to 0. Again, time response. Time response for t greater than or equal to 0 here, Vx of t. Then you have two types of approaches. One is the formula, the other is S domain. But S domain is not required here because it is a first order system. You see, Same time, it is it is excited by a step input. Understand all of you, okay? So therefore, you can comfortably go with the formula. What is that formula? So Vx of t, Vx of infinity minus Vx of infinity minus Vx of 0 plus into e power minus t by tau. So let's try to calculate one after other. Okay, let's try to calculate one after other here. Now, what is t equal to 0 plus conditions? At t equal to 0 plus conditions, that is Vx of 0 plus, okay, you need to go with t equal to 0 plus conditions. For that, you need t equal to 0 minus conditions. For t equal to 0 plus conditions, you need to go with t equal to 0 minus conditions first. Then you can calculate t equal to 0 plus. But here, look at this. What is this Vx? Vx is the voltage across the resistor. What is the procedure to find voltage across the resistor at t equal to 0 plus? Other than voltage across capacitor at t equal to 0 plus, if you want to find, definitely you have to go for step 2. Yes or no? For that, in step 1, you require current through the inductor. You have an inductor. Current through the inductor is required at t equal to 0 minus. So what is the value of it? Switch is what actually? Initially, open or close? T equal to 0 minus, the switch is open. Inductor is acting like a short. And our objective is to find the current through the short circuit here. If it is shorted, this is also gone. Then finally you are left with 10 volts, 2 ohm, 3 ohm in series, 10, 2 ohm, 3 ohm, and then short circuit because this is gone. So the current flowing through 3 ohm is nothing but current through the inductor. Therefore, you can find IL of 0 minus is 10 volts divided by 2 plus 3 because it is neglected. Yes or no, all of you? Why it is neglected? Can you visualize the network, all of you? Now it's a time to visualize the network, okay, for t equal to 0 minus. T equal to 0 minus you can easily visualize. Yes or no, all of you? Okay, inductor is acting like a short circuit. This is gone. If it is shorted, this is gone. You can't expect any current through 6 ohm. You can neglect that resistor. And then 10 volts, switch is open, right? 10 switch is open. 10 volts, 2 ohm, 3 ohm, and short circuit. That's it. So what is that 5 2 ja? That is 2 amperes you are getting here. And you are going to use this particular information in constructing t equal to 0 plus equivalent because your objective is to find Vx of 0 plus, where Vx is the voltage across the resistor. Yes or no, all of you, okay? So for that, let's draw the t equal to 0 plus equivalent circuit. T equal to 0 plus equivalent circuit. Okay? T equal to 0 plus equivalent circuit. What is that? 10 volt, 2 ohm, shorted, yes or no? Switch is closed. Resistor remain resistor. This resistor remain resistor. Inductor is acting like what? A current source with the value of. What is the inductor equivalent at t equal to 0 plus? A current source with a parallel inductor model. Yes or no? Okay. So what is this actually here? 2 amperes. That's it. So here your objective is to find Vx of 0 plus. Vx of 0 plus. So let me find this value. This is 3 ohm. This is 2 ohm. This is 10 volt. What is this value? 6 ohm. That's it. Okay. So how do you find it? Since it is shorted, if this is 0, this is also 0. Yes or no, all of you? Okay. So how these two are connected here? How these two are connected? Parallel. Or else you can do one thing. If this is 0, then you can call it V. Finally, you would like to find voltage across 3 ohm. Yes or no, all of you? Okay. So what is the voltage across 3 ohm? If it is 0, the voltage, if you take it, is V. Okay. Now this is also 0. The potential difference between these two can be easily calculated. Now Vx of 0 plus can be written as, since it is at higher potential, lower potential, but you want the voltage, okay, you want the voltage with this is higher potential, this is lower potential. Therefore, there is a mismatch in the polarities. You can say Vx of 0 plus is equal to what? Minus V. So let's find the V here. So what do you get here? V minus 0 by 3, V by 6, and plus 2. V minus 0 by 3, V minus 0 by 6. Okay, what about this leaving current? That's it. So what do you get here? V of 1 by 3 plus 1 by 6 is equal to minus 2. So what do you get here? Minus 2. Understand all of you, okay? So what do you get here? So 3 2 ja 2, 2 plus 1, 3 by 6, that is 1 by 2. So V of is equal to minus 2. So V is equal to minus 4 volts. And therefore Vx is equal to minus V. Yes or no, all of you? What do you get here? Minus V is nothing but what? Plus 4 volts. That's it. Plus 4 volts. Okay. So if it is plus 4 volts, then you need to find Vx of 0 plus infinity, because already 0 plus you have calculated. Okay. You have calculated t equal to infinite condition. So what is t equal to infinite conditions here? Vx of infinity. What is Vx of infinity? I would like to find Vx of infinity here. So let me draw the equivalent circuit. So what do you get here? Vx of infinity will be looking like this. This is shorted. Resistor remain resistor. This is also shorted. And here, what is this? This is also shorted. So look at this. This is an inductor physically available but acting like a short circuit. Now this is shorted because t equal to infinity, the switch is closed. Once you close the switch, can you expect any current here? Because the entire current is passing through this only. So what is this Vx of infinity now? Vx of infinity is 0. That's it. Now tau for t greater than 0. Okay, tau for t greater than 0. What is tau actually here? Tau is nothing but, okay, L equivalent by RTh. What is L equivalent here? Only one inductor is there, 2 Henry. What is RTh? What is RTh? Look at this. The switch is closed for t greater than 0. The switch is closed. This is shorted. So 2 ohm is directly appearing across short circuit, therefore it is neglected. Now through L equivalent terminals, when you look into the network, finally, okay, you are getting the 3 ohm and 6 ohm connected in parallel. Okay, that is 2 ohm. Therefore, you got tau is equal to, okay, L equivalent 2 by 2, that is 1 second. 1 by tau is also 1 second inverse. Is it clear, all of you? Then I think you got Vx of infinity and you got Vx of 0 plus, sorry, here Vx of infinity and Vx of 0 plus and tau. If you substitute all these in that particular formula, so Vx of t can be determined easily. What is that value? Okay, 0 and 0 minus of minus plus. So 4 into e power minus t. Okay, therefore Vx for all time t can be determined as, for t less than 0, for t equal to 0 minus, okay, that is, I'm sorry, here, t less than 0. What is t less than 0 here? T less than 0 is nothing but what? T equal to minus infinity. T equal to minus infinity means this is acting like what? Short circuit. Switch is open. Yes or no, all of you? Okay, switch is open. Then, if it is short circuited, and this is also gone now because of short circuit, this is gone. Finally, when it is opened, you are left with what actually here? 10 volt, 2 ohm and 3 ohm. So how much current is passing here? 10 by 2 plus 3. Already we found that value 2 amperes. Now 2 into 3 will give you 6 volts. So Vx of, okay, here I can find for t equal to 0 minus Vx of 0 minus nothing but Vx of minus infinity. How much here? 2 into 3, 6 volt. Okay, I need this information to answer this question. Okay, that is 6 volt for t less than 0 and 4 into e power minus t for t greater than or equal to. Okay, so please note down that. Okay, you can note down that, and meanwhile I just erase this and note down another problem here. Okay. Okay. So I think all of you understand how to calculate using that formula. It's very simple. More than 90% of the problems are asked in the previous GATE or IES or any competitive exams based on this formula only. If at all time response is asked in the exam, most probably the problems will be asked first order and step excitation. Okay. So note down that, and I would like to complete. For every instant, better you draw the equivalent circuit for your better understanding purpose. But if you have already understood how to really, okay, deal with the problems, and you can easily visualize the equivalent circuits easily without drawing the equivalent on the paper, I'm sure that you got a good expertise in that solving the problems. Okay, so therefore, in that case, no need to draw. But if you have any doubt, better you draw the equivalent. If you don't have doubt, okay, you can proceed. Okay. Eighth one, okay. This is another interesting question. So this is a question given. Four ohm and a dependent source plus minus 3i, 4 ohm, 2 ohm, 0.5 Henry. This is I and this is Ix. So now he is asking Ix of t. There is time response. Time response is asking, okay, Ix of t. Whenever time response is asked, our procedure is very simple. First we check whether the circuit comes under first category or second category. First category problems are dealt with a formula, simple formula, just now we discussed. Second category of the problems, okay, we deal with S domain equivalent. That's it. So look at that network, all of you. What is that actually here? Type of circuit? First category, right? Because it is a first order. And another is, it is excited by what? There is no independent source. There is no independent source. When there is no independent source, that means zero step input excitation we can assume. Yes or no? Therefore, first order circuit and zero step excitation, that means category 1. So formula can be applied. So what is the formula for Ix of t? Ix of t is nothing but Ix of infinity minus Ix of infinity minus Ix of 0 plus into e power minus t by tau. First, we would like to go with Ix of 0 plus. What is Ix? Ix is current through resistor. Current through resistor at t equal to 0 plus can be determined at step 2. But at step 2, in order to draw the equivalent circuit at t equal to 0 plus, we need current through the inductor at t equal to 0 minus. That is step 1. Okay, but he did not mention any switching operation in the circuit. Yes or no, all of you? There is no switching operation given. Unless you know switching operation, you do not know 0 minus conditions and 0 plus conditions. It's very difficult to find 0 minus conditions, or if at all the 0 minus conditions are given, it is well and good. Otherwise, you have to assume them 0. But what's happening here? Look at this. Assume I of 0 is equal to 10 amperes. I of 0, nothing but what? Current through inductor. Current through inductor at t equal to 0, nothing but 0 minus, nothing but 0 plus, all are same. Because current through inductor may not change instantaneously. That means, because he has not given switching operation, okay, he has provided an information that current through the inductor at t equal to 0 minus, Okay, if switching operation is given, probably he may not give you that information sometimes. Okay, or sometimes even along with the switching operation also, he may give what is the current flowing through the inductor at t equal to 0 minus. But anyway, in this problem, it's very clear that t equal to 0 minus, the information of current through the inductor is given, and he has not mentioned a t equal to 0 minus. So t equal to 0 minus, our objective is current through the inductor, we need to find, but it is already given, 10 amperes. Okay, t equal to 0 plus, we need to consider T equivalent circuit using this information. So what is that information? Current direction is clearly mentioned. This is an inductor, parallel inductor model. And what is this value? 10 amperes. And this is what the resistor. You are looking for current through Ix of 0 plus. And here is the voltage source. And here is the resistor. This is 4 ohm. Understand all of you, okay? So 3, what is this becoming actually here? I of 0 plus, what is the current flowing here? 10, 3 into 10, 30 volts. It is a voltage source. Okay, current dependent voltage source. And your objective is to find this value. Therefore, let's go for. So some Vx of 0 plus. Let's go with the node analysis. Vx of 0 plus of 1 by 2, 1 by 4 is equal to leaving minus 10 plus 30 by 4. Okay, so what do you get here? You need to find Vx of, okay, 0 plus. Once you find Vx of 0 plus, you can find what is Ix of 0 plus. Understand all of you, okay? You can find what is Ix of 0 plus. You can calculate that. Otherwise, I'll give you that answer here. I'll give you that answer. So that answer is minus 1 point. Let me just give you that value. Yes, you can find that value otherwise. Let us calculate it clearly. Vx of 0 plus, okay? What is that Vx of 0 plus? You can calculate Vx of 0 plus. So Vx of 0 plus, what is that actually here? 1 by 2 plus 1 by 4, 0.5 plus 0.75, okay? Or else you can say 2 plus 1 by 4, okay? 2 ja, 2 plus 1 by 4, 0.5 plus 0.25, nothing but 0.75. So is equal to, what do you get here? Minus 40 plus 30 by 4. So 4 gets cancelled, and Vx of 0 plus is how much? You get minus 40 plus 30 is nothing but minus 20 by 3. Okay, minus 20 by 3. And Ix of 0 plus is how much actually here? Minus 20 by 3 divided by, what is the current actually here? 2. So 10 ja. Minus 10 by 3. Ix of 0 plus is how much? Minus 10 by 3. I hope you understand the calculation part, okay? Minus 40 plus 30 by 4. Nothing but minus 10. Sorry, minus 10, okay? This is minus 10. Minus 10 by 3. And minus 10 by 3 divided by minus 10 by 3 divided by, okay, minus 40 plus 30, minus 40 plus 30, nothing but what? Minus 10. Minus 10 by 3 divided by 2, 5 ja, okay. So minus 5 by 3 is the correct answer. All of you please correct it, minus 5 by 3. So you get here, this value is nothing but minus 1.667. Yes or no, all of you, okay? So 3 1 ja and 3 6 ja again. You can calculate like that. Okay? So therefore, now tau for, or else Ix of infinity. Next one is what? Ix of infinity. You calculated already Ix of 0 plus here. Then next, let's go with Ix of infinity. What is Ix of infinity here? This is shorted. Yes or no? Okay. If it is shorted and this is I of infinity and Ix of infinity, this is 3 into I of infinity. But since there is no independent source at all, we already learnt when there is no independent source, okay, the current, voltage, power elsewhere in the given network is going to be what? 0 only. Therefore, Ix of infinity, okay, is 0. Okay, you can write if you want, since there is no independent source, the current will be 0. The tau for t greater than or equal to 0. Tau for t greater than or equal to 0, nothing but what actually here tau is nothing but, okay, L equivalent by RTH. Okay, L equivalent is how much actually here? 0.5. L equivalent is 0.5. But what is RTH? How do you calculate RTH? In case of dependent source problems, RTH, you have a special procedure, yes or no? You have a special procedure for, okay, calculating RTH in case of dependent source problem. Yes or no, all of you? So let's do that. Now let me connect a voltage source or current source, whatever it is, a source across the terminals where the RTH is to be calculated. So these are the terminals where RTH is to be calculated. So I am putting here a voltage source with the value of V, okay, and V dash, and some current it is delivering, that is I dash. Yes or no, all of you? Then here the resistor, remain resistor. Then this is another resistor. This is a very interesting point, okay? So this problem is really important. You can understand many things here. So 3 into, okay, you have I. Now this is what actually 4 ohm. This is 2 ohm. This is Ix. And this is I already given. Yes or no? This is I given. Now our objective is to find the relation between what? V dash and I dash and suppress all independent sources. Yes, there is no independent source. Whenever you find RTH value, the first step is what? Suppress all independent sources. But there is no independent source. Now these are the terminals across which we are applying the volt-amp technique. I think all of you understand what I am doing here. We need to go with only volt-amp technique. Understand all of you, okay? So volt-amp technique, what is the procedure? You are injecting some current into the network where the equivalent resistance is required by means of an independent voltage source. Now let us try to find it. This is 0 and this is what? V dash now. So V dash, okay, V dash, I can say minus I dash plus V dash by 2 plus V dash minus 3I by 4 is equal to what? 0. So equation 1, I need to eliminate I. But what is I actually here? I is equal to minus I dash. Because I dash is in this direction, I is in this direction, opposite. That's it. Substitute here 2 in 1. Then what do you get here? Minus I dash plus V dash of. Okay. Otherwise you can say, we'll simplify it in the next step. V dash by 2 plus V dash minus 3 I dash, that is plus 3 I dash. Because minus of minus plus divided by 4 is equal to 0. From this, I can say V dash of 1 by 2 plus 1 by 4. Okay. Now here you can say I dash of minus will become plus, that is 1. Plus will become minus, that is minus 3 by 4. Minus 3 by 4. Now what is this value? V dash of 3 by 4 is equal to I dash of 1 minus 3 by 4. What is it? 1 minus 3 by 4 is 1 by 4. Yes or no? 1 by 4. So 4 will get cancelled and V dash is equal to, what do you get here? V dash is equal to 1 by 3 I dash. So RTH value is how much here? RTH is nothing but 1 by 3 ohm. Therefore, tau calculation is what actually here? Tau is nothing but 0.5 divided by 1 by 3. So this is nothing but 1 by 2, nothing but 3 by 2 second. 1 by tau is nothing but 2 by 3 second inverse. Yes or no, all of you? Okay. Therefore, if you substitute that, all those things in the formula, Ix of t will become now, Ix of t will become now, Ix of infinity, nothing but 0, Ix of 0 plus that you have already calculated minus 1.667, okay, minus 1.667 into e power minus t by tau, nothing but minus 2 by 3. You understand all of you? Okay? You understand the difference between the problems on the same formula based. When the current is asked, instead of ix of t, for example, I of t is asked, the problem will become very simple. Yes or no, all of you? Because for I of t, I of infinity, I of 0 plus, for that you don't need to go for the t equal to 0 plus equivalent, because he is asking what is current through the inductor. But most of the problems may be asked, in the exam, okay, based on current through, okay, resistor or current through capacitor, voltage across the resistor or voltage across the inductor. You may be. So that's why I told you already, you must be expertise in drawing t equal to 0 plus equivalent. So in the transients, when the dependent source problems are given, this is how you need to really solve the problem. Understand? Okay. It's a very interesting model. So all of you please copy. All of you please copy. Then, if he's asking what is I of t, do you need this entire calculation? Not required, because I of 0 plus, what is that? I of 0 plus? Nothing but I of 0 minus. So 10 amperes only, that's it. This entire t equal to 0 plus equivalent is not required. But for tau calculation, RTH calculation, definitely this procedure is common to, okay, any response that is asked in the circuit, whether it is Ix of t or Vx of t or I of t or V of t, whatever it is. The tau does not change. Tau changes only when the switching operation changes. When the switching operation changes, the network configuration will change. You understand? Okay? When the network configuration changes, then obviously the tau value will change. Yes or no, all of you? Okay? So the tau is independent of the response that is required in the given network. But the tau is dependent on. The tau is dependent on what? The switching operation. If you change the switching operation, then tau will change. If you change the type of response, whether it is I of t, Ix of t, V of t, same network, switching operation remains same, the tau remains same. Understand all of you? Okay? Whether it is I of t or Ix of t, the tau value is same. The tau, determination of tau is same as it is. RTH calculation, dependence problem, you have to follow the standard procedure. I already explained you in the case of theorems, how to calculate RTH value. In the case of dependent source problem, the same procedure you are supposed to apply, okay, wherever you come across the procedure, wherever you come across the problems, whether it is transients or, magnetic coupled circuits or two-port networks, I'm sure that this procedure is going to help you a lot. Okay? Whole time technique is very, very important. So I think all of you are done with this particular part. So just only this part I will erase and you can continue with that. I just note down another problem here. Problem number 9 is also a very interesting question. I'm just trying to give you varieties of problems here so that in the exam, if the problem is asked in any dimension, you will be in a position to answer it. Okay, I'm taking different varieties. Okay, not the monotonic type, like only in the similar models. Okay, not like solving a number of problems in the similar model. I'm taking different models. Okay, so please note down that quickly. Meanwhile, I just note down the problem. I just write the problem on the board. Number 9. This is a very interesting question. So one must be good at visualization of the network for t equal to 0 minus and drawing the equivalent for t equal to 0 plus and also visualization of the network t equal to infinity without wasting too much of time in the exam, okay? You must be really good at visualizing the network. This is 10 ohm, this is 20 ohm, this is 15 ohm, 6 ampere. Okay, so classroom workbook question number 9. It's very interesting question. All of you just note down. The circuit first you note down. You need a lot of practice, I'm telling you. Transients is very, very interesting topic. Okay. Time response calculations are very, very important. After discussing this application of differential equations, we are going to discuss application of Laplace transformations. So the category 2 problems or type 2 problems, how we solve, that we will discuss. Okay, so let's have a discussion on it. First, you read the question carefully and try to understand it. I of 1, I of 3 is asking. Okay, what do you mean by I of 1? Okay, I of 1. How do you calculate I of 1? I know how to find I of 0 minus. I can directly construct equivalent circuit. T equal to minus infinity, I can construct. T equal to 0 plus, I can construct. T equal to plus infinity also I can construct. But can I construct I of 1 equivalent circuit? Not possible. For that, what you do is, you just find I of t. Once you find I of t, okay, you can just substitute t equal to 1 second or t equal to 3 seconds, anything that you want you can find. Understand all of you, okay? So therefore, first you find what is the time response. But the difference between this problem and the earlier problems, if you can observe, okay, the difference between this problem and the other problems is, here you got two switching operations. At different times they are operated. At different times they are operated. At t equal to 0, the first switch is operated. With some time delay, the second switch is operated at t equal to 2 seconds. You understand, okay? Now he is asking, what is I of 1 and what is I of 3? You can take an example of understanding in a better way. Okay? You can understand this particular problem by taking a simple example. For example, an elevator is there. Elevator is initially, okay, at t equal to 0, you are moving this elevator from ground to second floor, let us say. Initially, elevator position is assumed to be what? Steady state. You enter into the elevator and you push the button of second floor, let us say, or let us third floor, let us say. Your objective is to reach the third floor. You push the button of third floor. Understand all of you, okay? But until you enter into the elevator and push the button of third floor, then the elevator was assumed to be in what? Steady state. So initially it is in steady state. So it is in steady state 1, steady state 1, steady state 1, and you entered into the elevator, press the button of the third floor, that means you apply the disturbance. It will enter into the what? Transient, and after some time it will reach to third floor. Yes or no, all of you? Okay, this is 0 floor, and this is third floor. Okay, this is third floor, and it will reach again steady state. Yes or no, all of you? Steady state 2. Now you want to understand the dynamics of the system. Getting all of you? You want to understand the dynamics of the system before it reaches to the third floor. That is one object. Now again, after some time, somebody else entered to the elevator. Now, with a delay of, let us say, 2 seconds, he pushed the button of, let us say, 10th floor. He would like to go to 10th floor. This is the 10th floor. What will happen? It will again enter into transient state. Then finally it will reach what? Steady state. So steady state 3. Steady state 3. Yes or no, all of you, okay? Now I want to understand the dynamics of the system in between steady state 2 and steady state 3. Yes or no, all of you, okay? Now somebody else will come again here. We'll push the button of, let us say, 5th floor. Then it will reach to 5th floor. That 5th floor is nothing but steady state 4. What's happening? Continuous disturbance are taking place. Continuous switching operation are taking place. So this problem can also be visualized in the same way. Initially, the network is in steady state. At t equal to 0, the switch is operated. Then it is entered to transient state. And finally, it is reached steady state. Okay. Again, at t equal to 2 seconds, it is disturbed by means of switching operation. It will again enter into what? Transient state. And finally, it will reach steady state. Like this, the switching operation is taking place. You understand all of you, okay? But now the problem here is, he wants to analyze the dynamics of the system between the first switching operation and second switching operation, and the dynamics of the switch system or the network, okay, after the second switch is operated. I of 3 is nothing but what? At t equal to 2 seconds, the second switch is operated. That means after second switch is operated, what is the network, that is current? Current through what? Actually, inductor is asked here. Inductor, please note down this. I of t is asking current through inductor only, right? Now, what is the current through the inductor at t equal to 3 seconds? You understand all of you? Okay. Therefore, you need to calculate the I of t for okay, I of t for t greater than 0 and less than 2 and t greater than or equal to 2. I hope you understand the point. Okay. T greater than 0 and less than 2 and t greater than or equal to 2 seconds. So now if you know the responses here, this response and this response, and this response, if you know, you can substitute, okay, t equal to 1 second, that is t equal to 1 second, you need to take this response and substitute the t equal to 1 and get the value. Then you get the answer. T equal to 3, for this response, you substitute t equal to 3, then you get the answer. For that, let me write clearly, okay, the responses for t greater than 0 and less than 2, the I of t is calculated for t greater than 0, okay, t greater than 0, I of infinity minus I of infinity minus I of 0 plus into e power minus t by tau. Okay, so what is I of infinity, Nana? I of infinity in this context is what? For I of infinity, what is the switching operation? S1, okay, S1 closed and S2 open, yes or no? Don't say it is closed. You cannot say infinity is greater than 2 seconds. Okay, let us use the common sense that this is nothing but what? A steady state for which condition? T greater than 0 for and t less than 2. That means what? The network has already reached the steady state before the second switch is operated. That steady state condition we would like to know. So the steady state condition, that the current through the inductor at t equal to infinity in this context is, okay, when the S2 is open still, because the direction of the switch is very clear, it is not operated yet, okay, but S1 is operated. Therefore, S1 is closed according to the direction, S2 is still open according to the direction. Therefore, what is the value of it? The inductor is acting like a short circuit. Resistor is there because it is open, it is closed. Therefore, the network is something like this. The network is, it is looking like this. The switch is closed. The resistor remain resistor. This resistor remain resistor. And what about this? Short circuit. And you would like to find this I of infinity. Okay, so what is this value? 10 ohm, 20 ohm, 15 ohm, and this is 6 ampere. Therefore, this value is opposite resistance 50, because these two are in parallel, right? The 10 plus 20, 30 and 15 are parallel. Opposite resistance 15 by 15 plus 30 into 6. 15 3 jar, 3 2 jar, nothing but 2 ampere. I hope you understand the point, all of you. Okay. Next, I of 0 plus. Okay, I of 0 plus. What is I of 0 plus? For that you require t equal to 0 minus conditions. What is t equal to 0 minus condition here? S1, okay, S1 open according to the direction given. S2 is also open, and inductor is acting like short. When this is open, this is open. Can you send the current through the inductor here? It's not possible. Therefore, I of 0 minus is 0. Since I is current through the inductor, I of 0 plus is nothing but I of 0 minus. Without constructing t equal to 0 plus equivalent, you can find what is this I of 0 plus. Yes or no, all of you? Okay. Next, tau for t greater than 0 but less than 2 seconds. You understand? Okay. Tau for t greater than 0 but less than 2. You need to find. So what is that actually here? L equivalent is how much here? 5 Henry. RTH is how much here? What is RTH for this condition, Anna? Okay. This condition, what is this? S1 closed, S2 open, right? S2 open. S2 open. S1 closed and S2 open. Then what will happen here? It is closed, this is open, then L equivalent is 5 Henry and this is open circuit for RTH. When you are looking into the network, 15 plus 10 plus 20. What is this? 15 plus 10 plus 20. 45 ohm. Therefore, tau will become 5 by 45 by 9, 1 by 9 second. But 1 by tau generally is of your requirement 9 second inverse. Now you can substitute all these things and find the I of t. What is that I of t? Tell me. That I of t is, okay, I of t is, I of infinity is, what is the value you got actually here? I of infinity, how much you got? It's 2 ampere, okay, 2 minus 2 minus, what is the value? 0 into e power minus 90. So 2 if you take common, 2 of 1 minus e power minus 90. I hope you understand the point. This is what the time response for t between what? 0 and 2. Okay. Now, if you want to find I of 1, yes, you can substitute the t equal to 1 in this formula and get the value of, that is I of 1 is nothing but 2 into 1 minus e power 9 into 1. You will get, okay, let me give that answer. You will get, yes, exactly, that 1.999 ampere. That means what? It is almost close to 2 ampere. What is the steady state value? 2 amperes. Okay, at t equal to 1 second itself, the current has already reached, almost it has reached the steady state 1.999 and 2, what is the difference? Just 0.0001. It's almost reached the steady state value by the time t equal to 1 second. But when is that second switch is operated? At t equal to 2 seconds. At t equal to 1 second itself, the network has reached the steady state. Okay, and at t equal to 2 seconds, you are operating that switch. Okay. Now, what about your next question here? I of 3. For I of 3, definitely you require the response, the time response for t greater than or equal to 2. That is nothing but I of t is equal to, okay, I of t is equal to I of infinity. Let me write it clearly here. I of t is equal to I of infinity minus I of infinity minus I of 2 plus, I hope you understand this, into e power minus t minus 2 by tau nana. Getting all of you? This is what the response when there is a switching operation taking place at t equal to t naught. What is t naught here? 2 seconds. Okay. Now here I of t naught plus, nothing but 2 plus. So what is I of infinity? What is I of infinity? This is the steady state. Okay. After the second switch is operated, by the time the first switch is also operated. Operated means closing or open condition, it is closed condition. But what about this particular switch? It is also closed condition. Once it is closed, this element is gone because short circuited, and this is closed. 15 and 10 are left over in the network, and this is short circuit. The equivalent circuit will become like this. S1 closed and S2 is also closed. Therefore, the network equivalent circuit will become, okay, something like this. Switch closed. Okay. This is short circuit inductor and this is I of infinity. Okay. This I of infinity and this I of infinity, what is the basic difference? This is steady state after the first switch is operated. This is a steady state after the second switch is operated. By the time the first switch is also operated here. But here, the second switch is not operated. That means it is still its open condition. That is why 20 ohm is present. But here, it is closed, therefore shorted. The 20 ohm is, okay, shorted. This is gone. Therefore, what is this value? 10 ohm and 15 ohm. This is 6 ampere. Now, I would like to find this I of infinity. Okay, I can neglect it. Okay, what is the current flowing through 10 ohm? Nothing but 15 by 15 plus 10 into 6. Okay, so what is the value actually here? 5, 3 ja, 5, 5 ja, 18 by 5 ampere. Okay, 18 by 5. So you get that value. What about I of now 2 plus? I of 2 plus. I of 2 plus, to find that you require T equal to 2 minus equivalent circuit. Yes or no? Okay. What is T equal to 2 minus equivalent circuit? And what is this I? I is current through the inductor. Therefore, I of 2 plus is nothing but I of 2 minus. I of 0 plus is equal to I of 0 minus. Similarly, I of 2 plus is equal to I of 2 minus. But T equal to 2 minus conditions, let us try to find here. T equal to 2 minus. So T equal to 2 minus means nothing but what? Again, the network. Here the switching operation S1 closed. Okay. S1 closed. Let me write it clearly. S1 closed. Closed. S2 still open because it is 2 minus. At T equal to 2, the switch is closed, right? But 2 minus, it is still open condition only. And the inductor is acting like a short circuit. It is nothing but whatever the I of infinity you have calculated, okay, whatever the I of infinity you have calculated, understand all of you, okay? That is nothing but what? T equal to